to this very special week which we have celebrated for chemistry. And I would like to welcome, I think, many of our colleagues who are known to us here also. I can see from the list, I think Dr. D.V. Prabhu, celebration, who is also the chairman of BASE. I can see Dr. Jaya Pandey also, and there are many others who are known to us. It's really good to see all of them for this lecture, particularly on a holiday, just on the eve of Diwali. In fact, Nehru Science Center celebrated this from 5th to 11th as Chemistry Week, and we organized lot many programs, live demonstrations of experiments in chemistry, particularly. Then there were liquid nitrogen show, and there were many other experiments which people have enjoyed. There were online quiz as well, and right now also at our gate. Liquid nitrogen show is going on. Then we had, I think, a lab setup where DIY means do it yourself chemistry where 10, I think 10, 12 experiments were kept, and children or parents or groups, those who were coming, they could perform the experiments on their own. So, and today we are concluding this week. This is very special for us also, as you can see in the poster on screen. Today, Nehru Science Center has completed 38 years of its service to the nation. It was inaugurated on 11th November 1985 on that day by then Prime Minister Mr. Rajiv Gandhi. And since then, we have really come a long way in terms of visitors figures as well as number of people who are coming to Science Center for activities, programs. So we have traveled really a long journey, no doubt about that. It is all because of our audience and participants and all our well wishers, those who have supported us, who have guided us, who have mentored us, and gave their full unconditional support, I should say. So one of them is also Dr. A.P. Jayaraman, about whom you can see he is a former nuclear scientist. Post his service from BARC, I think he went to Singapore also in management services. There he was visiting professor. He is also the chairman of National Center for Science Communicators. He is also principal scientific advisor on HSNC University, which is in Mumbai itself. He is member of scientific committee on Public Committee for Science and Technology Network, which is a worldwide famous organization in terms of science communication, because Dr. Jayaraman himself is also a great science communicator. It's always a treat to listen to him. I'm a big fan of, personally, I can say that. And I think those who will be listening him today, they will also join me maybe in the next lecture in saying the same sentence which I have just said. He is also the trustee of Indian Development Foundation. It's a organization which supports lot many students also, and I think there are many schools with whom he is associated. Uh, in fact, last time when I introduced him, I could remember, I think there were some 8,000 hours which he has spent online and attended during, particularly during pandemic. He was so very active on online format, and we have also been blessed, I should say, by listening to him, by taking his services, by taking his favor. So today it's a very interesting talk. It's from alchemy to modern marvels. It's about chemistry, and I hope we are all going to be enriched a lot. Chemistry. Last time I used this. In fact, I read it somewhere in one of the lecture. I think Professor Prabhu told, chemistry is the science of matter, and chemistry is the science that matters. So it was, I think, it's a very good, and that justifies that why we are having this lecture from alchemy to modern marvels, particularly in chemistry. So with this brief background, I think I will request now Dr. A.P.J. Raman to take over and start his this. We are waiting for this wonderful lecture from alchemy to modern marvels. Thank you, sir. Over to you.
Hello, good morning, everybody. I am thankful to Director Mesh Kumar Rastogi ji for giving me this opportunity to speak about chemistry. I love chemistry, although chemistry doesn't love me so much. I am very delighted to be with the Chemistry Teachers Association because teaching chemistry is very, very important. I would also say that chemistry is life. Without chemistry, nothing. At birth, in life, in health, and in death. We are all doctored and nursed and treated by chemistry. No chemistry, no life. No chemistry, no matter. So I would like to do the story of chemistry, the history of chemistry in a storytelling mode. Long, long ago, once upon a time, in ancient times, in the dim distant past, in antiquity, there was a cave, and in the cave, there was a cave woman. She was just moving around the face of the cave. She saw a mammoth excreta, saliva. She took that saliva, that mammoth saliva. She saw some volcanic ash around, mixed the two. The first woman chemist, cave woman chemistry, and that was the birth of the now famous chemical shampoo. So that shampoo was created by the first cave woman who saw this mammoth saliva to which she added volcanic ash, which is a mixture of several metals, and that was the birth of chemistry. That was the birth of cosmetic chemistry also. So going back from the days of the caves, science improved slowly, very, very slowly in the beginning. Now it's growing very fast. We found that there were people who followed the footprints of the cave chemists and they created a branch of chemistry called alchemy. Alchemy means whatever they knew about matter, they wanted to change it from one form to the other, from a less useful form to a more useful form. That was the search. It was also a dream for them. They found many things around and they wanted to make them more valuable, more precious. So one thing which they wanted most was there were metals, small metals from the volcanic condensation. Lead was very common. How to convert that largely available lead into rare, a rich commodity called gold. So lead to gold, lead to gold, lead to gold. That was the slogan under which alchemists worked. But they tried all sorts of tricks, everything they knew. They tried concoctions, they tried very, many harsh methods, cold methods, hot methods, but lead never became gold. It was a brain that turned sour. Yet they continued. They continued their failure story. And today, we in nuclear chemistry will not be able to convert kilograms of lead into gold, but we still can convert an atom of lead into an atom of gold by a long tortuous procedure. It's possible. But we learned a lot from the alchemists. The other thing which the alchemists were very, very fond of was to make an elixir called Amrit, deathlessness, immortality. Man has a short half life. In those days it was 50 years, or 45 years or much less than that. People used to die very young. How to live without dying? Permanent life, perpetual life. That was the objective. And where did they look up? They look up to chemists. And that chemistry is also alchemy. Various liquids were added, they were distilled, concoctions and potions were made, they were tried, and of course we could not make an elixir which they wanted, but we made many chemicals. We made many pharmaceuticals. We made many drugs. So two things developed. Metallurgy from alchemy led into gold, and from elixir they went into different drugs and potions as they call it. So this is the greatest contribution in the beginning of the history of chemistry. So you will find the alchemists believe that they are not able to do it, but there is a white hair in the moon which can come down to the earth, and if it does some mixing in a mixer, This old mixer is a granite stone in which a wooden bar is being used. They could make it. So they always worship the white hair in the moon. The lunar white hair was the goddess or the god for the alchemists. They also tried a little of geometry. They put a circle inside the circle. They put a triangle inside the triangle. They put a square, and they again put a circle inside that. So geometrical combinations were tried. They were all mind-boggling experiments. You may wonder what chemistry has got to do with this. Yes, looking for that truck, looking for that gold, and trying to use symbols for that. This is how they moved on. Now, if you look at it, they also developed a sort of a language. Today we know H is hydrogen, H is helium, hydrogen, helium, lithium, beryllium. This is all known to us very, very well. But in olden times, in the days of yore when alchemists were flourishing, you will find lead and gold are written by these symbols. So lead is a four, old four, with an arrow, and it becomes a circle with a flying wing. So this was their ambition, their innermost desire, and they followed that. They couldn't do much about it. But today, if you want to make, you all know what mercury is. Mercury has an atomic number 80 and a mass number 197. If you can knock out, if you can throw out one proton from the nucleus of the mercury atom 19780, you get gold. But that's not an easy job. You have to do a lot of complicated chemistry for that. For example, you can start with the lead, atomic number 82, mass number 197. Remove a proton, you'll get 197, 81. Again, you go reduce one more proton, you get mercury 197. Another proton goes, and there you get gold. So the route from lead through thallium through mercury to gold has been established. Although you cannot start a company tomorrow, an entrepreneurship or a startup factory tomorrow to make gold in big numbers. That's not possible. Now here I am trying to show you some symbols. Symbols means something which stands for something else. Now, all those elements means the basic, fundamental, elementary part of it. They were described what is known to them. They couldn't do anything with water. So arsenic, antimony, magnesium, lithium, phosphorus, potassium, and water, aqua. They were all put in these forms. Instead of writing WAT, they put a symbol. Instead of writing zinc, they will write Z, and a dash on the base. So, production of symbols to stand for something, that's a big, big achievement in chemistry. Instead of writing hydrogen, you simply write H. Everybody will know H means one atom of hydrogen. So that is the beginning of symbolism or the shorthand way of writing chemistry. And that caught on. Today we have 118 elements. All of them can be described clearly and accurately, precisely. When you write H, it is H, hydrogen only. If you write He, it is helium only. There is no difference. So everybody will understand the same thing everywhere. This is what we call a universal language, understood by all chemists all over the globe. So to have a language, to have words, to have symbols, then to have a grammar, and then to use sentences, that is what chemistry is. This is the alphabet of chemistry. So we have 118 elements with which the entire cosmos, apart from other planets, can be understood chemically. So we are very, very lucky. Today we can understand the whole universe in terms of chemistry. But from
तो ये तो सवाल
alchemic
पूछेंगे, सवाल
chemistry
निकाल के रखो।
to scientific chemistry, it took a long time.
आज it ask questions.
Science was not known thoroughly, and science was only evolving. It was taking its baby steps, tottering steps to become a nature science. On the front of that, we find the father of chemistry, Robert Boyle. It's not good to call him father of chemistry because then they will say, where is the mother of chemistry? So it is better to call the architect of chemistry or the creator of chemistry, Robert Boyle. His major problem was what do we do with gases? So he looked at gases, and all of us study the standard, this is standard for Boyle's law is increase the pressure, volume decreases. Decrease the pressure, volume increases. And multiply the two, pressure into volume, a constant. So that law, pattern, regularity, something which can be reproduced by everybody at any point of time, not known to some scientists alone, it can be done by anybody. So science became democratic, science became reproducible, and pressure volume relationship was valid throughout the world, not only throughout the world, of course, throughout the universe. So this universality of scientific principles was established by chemist Robert Boyle. Now I'm just going to Antoine Lavoisier. Antoine Lavoisier is one of the first scientists whose wife helped him in the laboratories. It was the chemistry couple. And Lavoisier is famous for his theory of how do we burn something? If something burns, what happens? Today in our classes, in chemistry books, we don't study a word called phlogiston. We never think about it. In fact, science rejects its unwanted things, refines the finest, and takes it forward. So we speak about Oxford. So if something burns, then we should know how it burns. So understanding those very basic facts, that's what these two great men and the great lady did. And chemistry became, from alchemy, it has matured, graduated, or I would say undergraduate, to scientific chemistry. What does science mean? Science, in very simple elementary terms, enables you to know things and to do things. Knowing and doing are the two hands of science. But what happens in science is many people know many things, they don't do. And many people do many things without knowing what they are. So knowing without doing and doing without knowing, both are anti-scientific principles. Although knowing and doing are the fundamental aspects of science. We should learn this elementary truth as early as possible in the elementary classes so that we know something and we do that. And when we do that, we should know something more. This equation between knowing and doing and going forward, that is what science is, nothing more than. So you looked at the dream of the alchemists. They wanted to put everything in symbols. And the modern alchemist, and most of us today, will be having our periodic table. That periodic table is a rich repository, a gold mine of all of our knowledge. Everything that is known to us, including some things which are not known to us but which will be known later. The discovery will fit into a pattern, a beautiful pattern, recognition of patterns, reproduction of patterns. That is another aspect which chemistry could successfully do. So if you look at the periodic table today, from hydrogen, element number 1, to organison, 118th element, we have the whole thing folded in front of us. Not only that, we know their names, we know them with acquaintance, we have good familiarity with them, we have good acquaintance with them, we know them. Not only we know them, we can make them do the work like a workhorse. Which will combine with what? How will they combine? What will be the nature of the product? What will be the properties of the product? Everything can be understood in a very systematic way from the periodic table. So that's the elemental periodic table from hydrogen to organison, from a gas, simplest gas, from the most abundant in the universe to the rarest gas, organison, a few atoms, 2, 3, or 4 atoms were made in that. So that's the story about the periodic table. Here is the periodic. So there was a few years ago we celebrated the 100 years of the periodic table. So I had personally the privilege of writing a book, a story, 118 stories on each element from hydrogen to garrison for children under the age 12. And we wrote a book. And when we wrote a book, the Royal Society of Chemistry at London thought they would like to have a look at it. So I had the privilege of meeting Martin Polyakov. He is the man who has given you 118 YouTubes of all the periodic elements, all the elements in the periodic table. And another interesting chemical story about him is one of his hairs was plucked, and the periodic table was inscribed in his single hair and retained as a rare curiosity in the Royal Society of Chemistry. So that's the green chemist. He is wearing a green tie and a green shirt, and there's a reason for that. We'll come to that when we speak about green chemistry. So periodic table taking what we discussed was how to take the periodic table in a story mode to all the children. Children under 14 should know the names of the elements, some of their properties, how they interact with your life. So that was the great story of the story of periodic. Now, at the base of the periodic table, at the heart of the periodic table, we have the atom, atomos. And atom means atomos, uncuttable. You cannot cut it. An atom remains as it is. You cannot split it into two. That's what chemists told us. And we all thought the atom, we were trying to understand the atom, so there is no question of splitting something. So first we tried to understand. And we had two great men, J.J. Thomson. He said there is a small, tiny electrical particle negatively charged which is moving around. Oh, motion, negativity, and a tiny particle. The concept of an electron as a bit of matter was introduced. The moment negativity came, somebody was naturally and positively looking at positivity. And Rutherford said, hey, that negativity is balanced and neutralized and gets stable in equilibrium by a positive spot, which we call the nucleus. So the atom, the uncuttable atom, became two pieces. We have an electronic cloud around it, and inside we have a positive nucleus. So the atom had a structure. It's not unstructured. And we were trying to understand, delve deep into the heart of the matter. After understanding the various atoms known to the alchemists, we went into a step forward. We looked at one atom, the carbon atom. Because in the universe, look at our own sun. Every time the hydrogen atom combines with itself and forms a helium. So hydrogen, helium, lithium, beryllium, boron, carbon. Up to that the whole goes. But carbon dominated. And the study of one atom's chemistry became a huge topic by itself. And that is called organic chemistry. And we can find that organic chemistry, if there was a scientist called Wohler, he said, I can make organic chemistry of the products, chemical products, which comes out of living organisms. The bacteria, the dog, the elephant, the man. These are all organic compounds we produce, they take in and take out. For the first time in the history of chemistry, we got an intuition from an inorganic compound, ammonium thiocyanate. I'll just heat it and I'll make an organic compound. Making urea from inorganic material was an epoch-making situation, and a new branch of chemistry was born that is called organic chemistry. Today we have millions and millions of organic compounds, and we can make any more. As a tailor makes your dress, we can go on with that. That should help us to look at Diwali chemistry. Now, Diwali chemistry is very interesting. Yesterday only we were looking at Diwali chemistry. We all have a matchbox. Without a matchbox, there is no Diwali chemistry at all. And if you look at closely your matchbox, on the side of it, you will find a brownish dark layer, hard and rough. And the wooden splint which you have with a red head, earlier in my school days it was black, now it has become red. And if you strike that, you will get the fire. That is pyrochemistry, making fire. Our old ancestors were taking two pieces of stone and hitting them one other. It's very hot with all their might. Then they could get a spark. And they used to keep a dry leaf or some cotton so that it catches fire. And making fire was a very difficult thing. That is why Atharva brought fire from the heavens. Or Prometheus brought it for the Greek civilization. So you need divine intervention of an unimaginable magnitude for bringing fire. Fire was a rare commodity on the surface of the earth. But today, we can make fire at our convenience. We can control fire. In fact, we are more worried about fire stations. We have strong fire stations which will control fire. Making a fire at home through a matchstick, pyrochemical break, has become very, very simple. The head of the chemist, there will be potassium chloride, KClO3 is to be used, and you will have a little red phosphorus on the head with antimony sulfide, and together those things will make you very convenient way. And there's a huge study in the match. Some of them can do it beautifully well. It's a skillful art of lighting, and learn that art safely. That's what we do. Then, after striking the match and making the fire, which Prometheus and Atharva found it extremely difficult, we set fire to our Diwali year. And that contains paraffin wax, CH3, CH229, CH3. So that wax, the white solid stuff which you see in your dimmer, is entria contained, an organic compound whose formula is known to us very well. Into that white matrix, you put a wick made either of cotton or cellulose, and that will be C5H10O6. That's the formula. And when you light the matchstick and set fire to that, the propagation of fire takes place and you get a flame. It's not enough, we are not satisfied with the flame we get. Of course, it's a beautiful dancing flame and it will be yellow. And if you don't have air, it will slightly dance to the left or to the right. So you look for your crackers and you have pyrochemistry at its best in crackers. You have to be very, very careful because firecrackers put bursts at unexplained places and put cause burns. There are strong laws which prohibit you from doing that. But still, out of curiosity, for amusement and fun and frolic, we do that. And it's being done all over the country and all over the world. Yes. But Diwali has seen a lot of it. If you look at the chemistry of the firecrackers, you will find that potassium nitrate, ammonium chlorate, ammonium nitrate with the carbon, that is fine powder, charcoal, absorbent carbon, and other things. So this is the recipe, the cookbook for making your firecrackers. Pyrochemistry has been very, very entertaining to us. We enjoyed showing pyrochemistry. And in Diwali, we had intimate encounter with a lamp. So you must study the chemistry as it happens in Diwali. So that is entertainment chemistry. Now we come to life chemistry, the chemistry of industry. The chemistry of industry is a huge one. Those who are in Mumbai can see the petroleum refinery complexes in the Atomby area. And you look at night, you will find the illumination from those distillation towers. The world will come to a grinding halt in a second if the chemicals are not produced right. That is our critical dependence on chemistry. No chemistry, no moment, no life. The whole world comes to a dead standstill. And the industrial chemistry, they make not only petrol and octane and gasoline and then a lot of other chemicals, use pharmaceuticals, food chemistry. The branches of industrial chemistry are too numerous to be encountered, but just remember the industry, the trade and commerce in which we live. The world is designed by trade, commerce, and industry, and that industry is driven by largely chemistry. I think we should look at the Roti chemistry for a short while. We all work hard to make a career, to make a profession, and to become the finest chemist. Why? to have the finest idea. So that comes from, if you look at the Roti chemistry or the food chemistry, you will find we drink water. We drink 2 liters of water. We drink 2 liters, minimum, although we should drink 4 liters of water. So that water is a chemical substance, dihydrogen oxide. Now the dihydrogen oxide in the mind of the chemist is a pure substance, colorless, odorless, tasteless, excellent. But there are 100 different types of waters, from aggressive water to condensed water to heavy water to zero water conductivity. So each water, the 100 different brands of waters are defined and described by their chemistry. The water is not one substance in the industry and at home, and the distilled water, sterile water, which we use for injections. So the chemistry of water is so great. We have water chemistry, and there are hundreds of scientists working on water chemistry with brilliant academic techniques. So that work in Roti chemistry, water is very important. The purity of water, uncontaminated, pure, drinkable, safe, potable water. Providing safe, potable water to 8 billion people is a challenge to chemistry. Providing safe drinking water, potable water to 8 billion people on the surface of this planet with a salty sea around us is a challenge. And chemists are now developing membrane technology and desalination technology to give safe water. So after water, we need to cook our rice and wheat, and the rice and wheat which we eat are carbohydrates, and they have chemical composition CX, H2OY. The X and Y can change depending upon the length of the molecule. So they are carbohydrates. There is carbon in that. There is hydrated carbon. There is water. So we need rice. We need 2000 calories of heat energy to come from this. Because every human being, all of us are 100 watt thermal machines. And therefore we need an input of energy. That energy comes from our carbohydrates. Now eating rice alone or wheat alone will not help us survive. You won't have a healthy body with that. So we need proteins, and proteins are amino acids. So the chemistry of protein should be understood very well. It's not enough if you have carbohydrates and proteins. We should have fats and oils. And let's look at the coconut. That coconut will be used stearic acid, C17H35, COOH, or oleic acid. So we get fats, ghee. That's all ghee. Now it's not enough if we have carbohydrate, water, protein, and that's life will be incomplete and dark. Therefore, we need vitamins and minerals. And let us look at the simplest usable vitamins. Vitamin C is C6H8. So that's the Roti chemistry. And you can delve deep into food chemistry, and if you go dig deeper and deeper and deeper, you can become one of the finest food chemists of the world. It's an enormous opportunity beckoning you for a bright day. It will now be good to look at the chemical price of our body when we die. In fact, there is a great philosopher, a American philosopher called Bertrand Russell. Sir Bertrand William Russell, fellow of the Royal Society. He was asked, Russell, what is life? And he gave one of the funniest, and probably the finest, and probably the most philosophical, mathematical answer to our human body. And he said, I quote, we are a few complex molecules of impure carbon and water. We are a few complex molecules of impure carbon and water, impotently crawling on the surface of an imperfect planet. That is a beautiful philosophical discussion on life and its metaphysics by Bertrand Russell. Knowing that we are all a few complex molecules of impure carbon and water, we can calculate our price. And in the chemical commodity market, we can go. And in 1922, Charles Mayo calculated our value, carbon, hydrogen, oxygen, nitrogen, and he said it was costing 2 rupees 65 paise. Okay, but there's an error. He calculated accurately, and human body in elemental form will cost you 2 rupees 65 paise. Later, some of his colleagues reworked on it and revised the number to 3 rupees. And therefore, we are owning up, or we are the proprietaries or owners of a 3 rupee value bond. But then the American Chemical Research Society thought we should have a closer look at the figures. And they came with the figure that the value of the chemicals composing the human body is rupees 1000. From rupees 3 to 1333 times, that's a fantastic magnification and multiplication. Later, people started looking at organic chemistry and biochemistry and the refined chemicals being made by the human body, and they found that hemoglobin will cost today's market price 2000 rupees per gram. Follicle stimulating hormone will cost 3.2 crores per gram. And another hormone called prolactin will cost 116 crores per gram. If you put, of course, we don't produce 1 gram in there. If you put the value FSH, follicle stimulating hormone, 3.2 crores per gram. So calculating the amount of hormones generated by a standard human body, we could find out that we could cost us about 365 crores. And we can also get that same amount if we sell all the organic tissues to the body. So this is a chemical calculation, the commodity price of the organic and biochemistry of our human. Oh, this is just when I was speaking about many chemists, their names, just remember there are famous human scientists who have done independently to it. Okay, we saw Roti chemistry, we saw. Now let us see Makan chemistry. See how do we look at Bombay? Just look out of your house, you will find tall, towering structures, all made up of concrete and steel. And that cement, which is the basic raw material from which these big buildings are bought, that is a tricalcium silicate. With the tricalcium silicate and with the tricalcium aluminum. So you will find the chemical composition of the cement, the binding power of it, that is used for making the buildings. It's not enough if you have cement, you should have good quality clinkers and sand. Some people use the white sand in the interior or use the black sand. So no matter whether the sand is white or black, of course it matters a lot in terms of chemistry whether the sand is white or black. If it is black sand in the 5 kilometer wide belt at the Kerala monocyte sands, it is 500,000 tons of thorium, the richest resource of the black sand in the world. You can also find it in Guadalajara. So what sand matters a lot. Don't use black sand for this purpose. And we need steel. Steel is iron to which carbon has been added. So it's all chemistry playing. Iron and carbon in different, and depending, and if you add a little more chromium, the strength multiplies maddeningly. So the business of a chemist is to make high strong materials. And then you want paints, thinners, additives. So without that, the building will not work. And what with the most modern buildings you will find glass, sodium aluminum silicate or borosilicate. So look, when you see a building, the chemist in you should get up. And look in organic chemistry, silicate chemistry, organic chemistry, biochemistry, all chemistry will flash into your mind the various fields. So when I look at a house, the chemist in me will look at the components of the house. Look at Kapda Chemistry. If we go into Kapda Chemistry, we can use either cotton, maybe many of you have got cotton sarees, we can have silk sarees, we have got nylon sarees. These are wonderful chemical steps. See their chemical structures. Fantastic creation of the human mind, the human brain, the neurochemistry of the human mind produce these chemicals. Remember, it is the neurochemistry of the human brain which produced these brain substances. Cotton structure, elucidating the structure of cotton. And the beauty of silk and the beauty of the equation to the chemist both are the same. The common man, this is the beauty of the silk, which is the irresistible attraction. But for the chemist, it is that glycine, alanine fluctuation in the molecule which is the most interesting. Not being satisfied with what Mother Nature gives. Mother Nature is giving us cotton. Fantastic. In the hot season in India, it's exceptionally good. But not being satisfied with a simple cotton, we have gone into silk, which we have made from silk. Then we have gone to now a multiplying array of other textile chemicals, beginning with nylon, rayon, and so on. So that is our Kapda Chemistry. And a textile chemical, if you become a textile chemical engineer, you will be one of the finest brains of our times. I want to tell you a little about nuclear chemistry, where I spent 40 years of my life. And the atom was called uncuttable atom because Canada said it's uncuttable. Greeks said atom was. But this great lady, this Meitner, she took an atom of uranium 235 with 92 protons. She heated with a neutron. For a moment, the neutron remained inside the uranium, adding to its mass. That uranium atom became a mass number of uranium 236. For a while, it vibrated in a turbulent vacuum. Thereafter, it split into two daughter products. The mother uranium 236, became two daughters, barium and tritium. It is not that the mother gave birth to two daughter products, it also released three neutrons. Those three neutrons went and hit three other atoms, producing 9. 3, 9, 27, 81. There runs the quick chain reaction. The atom was split. And human personality also was split in the process. And today, if you control this reaction, this Meitner's fission reaction, you can get electricity from a nuclear reactor. And if you do not control this reaction, just allow it to proceed in its vagabond way, then you get the nuclear bomb, the Hiroshima, and the Nagasaki. So the atom, another atom, which uranium 235 was converted into 236, and the barium kicked on, and the daughter products, and the three neutrons coming out, and there is a small mass effect, which is called delta L, which became energy, and that became the nuclear binding electron. And if that can be controlled, you can illuminate the whole earth with electricity, nuclear electricity. And if you, in a moment of madness, would allow that to continue uncontrolled, it's a violent explosion, then you have the Hiroshima and Nagasaki. Most of you would have seen the Oppenheimer film. If you have not seen that film, and you will get to a chance story of a scientist working on this. Now, there is another branch of chemistry which I call which we call the quantum chemistry, and we have Heisenberg and Niels Bohr as the architects of this quantum chemistry. The most fundamental curious problem which a quantum chemistry has to consider is this: can you think of a cat which is dead and alive at the same point of time? You will either see a live cat kicking, or you will get a dead, motionless cat. You cannot think of. It is impossible for the human mind to conceive of a cat which is dead and alive at the same point of time. That is what quantum chemists do. Quantum chemists have that remarkable capability to think of, to picturize, to visualize a cat which is living and dead at the same point of time. When you reach that intellectual elevation, you will be a good inhabitant of the quantum chemistry universe, and the future belongs to that. Future belongs to quantum chemistry. Of course, at the moment, our immediate need is green chemistry. Chemistry is red, it's violet. Some chemistry is very red, some are redder, and some are reddiest.
Be ready to ask questions.
To make it sustainable chemistry, we have ambassador. She has been responsible for coining the word sustainability. Sustainable chemistry is that chemistry when we use the present materials in such a way that our children and grandchildren will also have enough chemicals to work with. We don't eat up everything. Unfortunately, we are eating up the earth at a faster rate. In 1 hour, we are using 1.5 hours resources. We are using resources in a maddening way, with no care, no concern, no consideration for the futurity. So material should be less used, energy should be consumed less, and making chemical reactions which are green, using less energy, less materials. That is what green chemistry is, and Martin Polyakov has done it wonderfully well. So future, you're all very young students. When you go up, you will be speaking not about the red chemistry of my times in the laboratory. You will be speaking about the green chemistry of the future. Today, when you go to biology classes, you study only the living things which exist in nature, the plants, the animals, the plant kingdom, animal kingdom, or life sciences. But in future, 4 years from, 5 years from now, you'll be creating, synthesizing plants, cells, animal cells, and plant cells. So that is called synthetic biology. And if you want to be a good synthetic biologist, you have to be a good chemist. So chemistry is the gateway, is the door which opens you to the wider world of progress and prosperity. Then we go to the small world. Small is always beautiful. And in the small world, first we have microchemistry. Now we have nanochemistry. And nanochemistry opens the world with the wonderland of different forms of materials. And we are now trying to tailor drugs and pharmaceuticals, which will go and deliver the medicine exactly to that part of the body where the disease is. If you have cancerous growth in the liver, the nanochemically targeted molecule will go straight into the place where it is to do action oriented on the spot. So such things, small is beautiful, and nanochemistry is the future. If you look into the what will after 10 years when you graduate, you postgraduate, when you doctorate, and when you come to the world of chemistry, you will get, you will work on these fields. Nanomaterials for targeted delivery. You'll be seeing green everywhere, all the red will go. And you will make artificial food synthesis. You will not wait for the rice plant or the wheat plant to make wheat and rice for you. You will have your own machinery. Carbon dioxide and water will combine into the appropriate chlorophyll. You will have other nano catalysts in place of chlorophyll. You will be tailoring your food. And not only that, same material can be hard and soft at the same time. You will be able to program your matter and chemistry. And you will be making molecular machines, supramolecular material, and quantum chemistry. So that is how the world looks. If you look into the open window to the future of chemistry, bright and glorious, magnificent and majestic, and the world will be more lovelier and more beautiful. We should remember right here in India, Indian chemical market is 18,000 crores today. In 2 years, by 2025, it will be 30,000 crores. Okay. It's an enormous opportunity. A brave new world of chemistry is waiting for you. Study your chemistry. Listen to your chemistry teachers in great attention, rapt attention, undivided and concentration. And you'll be preparing yourself for one of the finest magical chemical careers of the world. I wish you all the best. Thank you.
Thank you, sir. As I said, it is always a privilege, or I should say, to listen to you for the wonderful lecture, the way you have connected means chemistry on a much bigger canvas of various type of chemistry, and the way you put up this Roti, Kapda and Makan chemistry means something I could recollect from that Manoj Kumar made one film on Roti, Kapda or Makan maybe in 1970s or late 70s. And now again, we are now connecting through chemistry, Roti, Kapda and Makan, and covering from Alchemy to the market of 30,000 crores in 2025, much wider. So I think we have audience also. Let us go to them and open this session for a few questions. We have time. Rajesh, we can have, I think, people are there maybe on side by side or maybe on screen. And let us see some questions people have sent, which Rajesh has shared with me.
Yes, sir.
Meanwhile,
There
yeah,
was yeah, one student
uh,
from Innovation Hub want to ask a question.
okay. So you what you can do, you can means we can request her to stop the sharing,
Yeah.
and let us take them online and on screen.
Yes, sir.
I think there will be many questions. I'm sure about that.
Yes.
So let us start from innovation of the young scientists. Those who have the question.
Ask.
I have a question that in Roti Chemistry, even proteins are there in the atta of the roti. And proteins are destroyed by heating. So when we make the roti into edible form, we put it on the tawa. Doesn't the proteins, don't they like get
Destroy.
destroyed due to the heat?
Oh, that's a wonderful tree. You can have carbohydrates, proteins, minerals, fats all combined into one molecule. And a tailor-made design molecule you can just swallow in the morning. And that should meet all your bodily requirements. So it is not beyond biotechnology to conceive and deliver such a material for you. You must work on it to have a capsule which will give you your requirement of carbohydrates, proteins, minerals.
Sir.
Rajesh,
Yeah.
Rajesh, you are
Sir.
mute. I think by mistake everybody has been muted.
Yeah. Sir, please
Uh,
unmute. Yeah.
yes,
Sorry.
sir. Sorry.
Sorry,
Just
sir.
continue, sir.
No, but I'll start fresh or they're not heard. Am I right?
Yeah.
Yeah, you, when you are talking about, it means you can make your own capsule. Up to that, we could have.
Yeah. A tailor-made person-specific dietary capsule is well within the means of biotechnology. And you will be able to calculate exactly your body requirements with a nutrition's help, design, and have it. That science is not out of the reach.
I think it will be a good way to fight obesity, which is
Yes, yes.
wonderful, wonderful. Any other question, or we can go switch on? Rajesh, anybody else would like to ask from our innovation of members?
Anyone? No. No, sir.
Okay, let them think. Let them think. We can switch over to our audience who are online from on their screens. So, anyone, Dr. Prabhu, would you like to have? I think I'm sure you must be having some question. Dr. Prabhu is the chairman of BASE right now. Yeah, I'm very well associated, and he's also from chemistry background. So it will be good if we ask some question. Sir, please.
Excellent lecture, Dr. Jayaraman. I've heard you before, but this is really a wonderful lecture which you have given. I think our audience will get an idea how versatile chemistry is, and how it can be linked with other subjects. You mentioned about this alchemy conversion of lead to gold, and I was really impressed by the series of reactions you have given, in which lead is ultimately converted to gold by intake of beta particles and expulsion of protons. Do you think this reaction can be done on a larger scale? Because that would mean conversion of lead into gold.
No, sir, it is not possible because
Okay.
half-lives of some of the intermediate
Okay.
so small, you cannot get 1 gram of
Okay.
lead of that isotope prepared. This is only
Okay.
a theoretical possibility. We cannot
Okay.
do a startup on this.
We cannot do that, yeah. Yes. But I was impressed by the equations you had given.
On textbook,
Textbook, yeah. On paper it looks feasible, but as you said, may not be
correct.
possible practically. Thank you.
Yes, sir.
But another interesting in that equation, I could correct was that at that time when they have started, means when they were trying to convert using mercury or means through alchemy metal to gold, and now it seems that now as you said, now we know about this chemistry. But it
Yeah.
seems very means so simple. Just it's a matter of one proton exchange of maybe, but it always not. That's what in books also sometimes we read write some equation which seems very simple, but in the background, so many things happen which perhaps is not visible, and perhaps we are not able to understand that.
Yes.
Yeah, really nice. Yeah.
Good.
Dr. Jaya Pandey, are you there? Yeah, really nice to see you. We have worked together in Lucknow, sir. And she has joined, he's, I think, working with MIT University in Lucknow. I'm really happy to see her. I requested her. She's also does a lot of chemistry experiment demonstrations we have done in Regional Science Field Lucknow. I'm really happy that she's here. Please, yeah, please your comment, Dr.
Yes, sir.
Jayapal.
Thank you very much, sir, for the kind introduction. And first of all, I would congratulate both the host, you, and the guest, Jayaraman, sir, for delivering such a beautiful and interesting lecture. And so many beautiful topics were covered in it. I have a little question from sir. I want to have little more insight about the green chemistry that he mentioned. So my question is, what is its status, present status now, and what could be the future vision? How we can take up green chemistry for sustainable development goals, and what could we do in future? On which way are we moving forward in green chemistry, sir? Can I have little insight more?
That's a beautiful question and also an equally complex question. The simplest form, every chemical reaction should use less material and should be done at lesser temperature and lesser pressure. For example, we are doing desalination. We are removing salt from seawater. Seawater contains 35,000 parts per million of sodium chloride. We can do distillation, enormous, but that means seawater is being raised to a temperature of 100 degrees Celsius and then converting into steam. That's a very energy prohibitive process. If you do it by membranes, semi-permeable membranes, we can reduce, but then pressure is applied. But RO process, reverse osmosis process of desalination is a little green compared to distillation process. Still, there should be another method by which we should be able to reduce the pressure. Therefore, every chemical reaction should be weighed in the grudging scales of matter and energy. Less matter, less energy. Ammonia synthesis. You are using nitrogen and hydrogen under the hyper process at high temperature, high pressure reaction. We cannot afford high pressure, high temperature chemical reactions in the surface of this planet. Energy is costly, matter is costly. So you must think of softer, gentler chemical process, and that is green chemistry. And today, every reaction is being weighed in that. All industrial chemicals are being looked after for their energy content. So that's the main. And there is a green chemistry is an evolving field. Now, as degrees, all the 17 degrees are linked into that. And the future is very, very bright for green chemistry. But from green chemistry, we have to go to greener chemistry and greenest chemistry.
Yes, sir. So, sir, I understand that we have to find ways to change the chemical-based materials in the industry to the nature-based solutions, as you have guided right now. And there is, I feel there's a tremendous scope of scientific as well as commercial opportunities, which lies in the field of both renewables, use of renewables, and the use of green chemistry, and the young minds which are sitting with us, and the younger and the future generation will, I think and hope, certainly take up such challenges to give us the greener solutions and solve many of the problems related to pollution as well. Thank you so much, sir. It was wonderful. Thank you, sir.
Thank you, Dr. Jaya. Now, anybody else has raised hands? We can take the questions because I can see only a couple of people on the screen. Anybody would like to ask question to Dr. Jayaraman? Okay. I have one question which Rajesh has shared with me by Saranya P. What makes chemistry so unique, and what are some ways that chemistry help us in our daily lives that we are not aware about?
Chemistry can help us in several ways. In the water, the purity of the water we drink, the purity of the food we eat, the chemicals which we use, the school bag which you take to your school, including the lead pencil which we are using, any material which you come into contact, for example, the leather shoes which you wear or the plastic shoes you wear, right from our hair to our foot. Think of any matter which you are applying soap on your body. Now, what is that soap? Sodium and stearate. Now, if you use the sodium stearate and use hard water, you get a scum on your body. So, every material, including air you breathe, the particulate in the air, carbon dioxide in the air, the oxides of nitrogen. See everything from the spectacles of chemist and see whether that chemistry, and remember every chemical, no matter what it is toxic. Toxicity is the main property of every chemical, including that of water. If you drink 2 liters of water, there is no problem. But depends on if you are injecting 2 liters of water directly,
सब पता है
it's going to split your leg. So water is a poison depending upon the point of entry. You drink, it's fine. If you are injecting directly intravenously, so many liters, there's a problem. So chemicals and their use
क्या
should be seen very, very clearly with respect to the damage, potential damage it can cause to you. Whether it's the water you drink, the air you breathe, or the drug you take, evaluate everything. And remember at the back of your mind that every chemical is a poison. It's not that everything is potassium cyanide. In a small quantity, the chemical becomes a great poison, but in larger quantity, by accumulation, bioaccumulation in the body, it can create a disastrous effects. Understanding chemistry is very important, not only in our body, to our body, and into our environment. Because our living is a chemical process. Every human being is a chemical reactor. It reacts with its environment, and that interaction will produce undesirable effects if you do not know your chemistry. Study your chemistry.
There is one more question from Somnath Santram. As we reflect on the evolution of chemistry, how do you envision the future of the field, especially in terms of emerging areas of research or potential breakthroughs that might reshape our understanding and application of chemistry?
Yes, our future, if at all we have a future, will be decided on sound effects.
देख रहे हो तुम लोग लाइव में
If you burn all the carbon and petroleum material here and you are going to have a civilization based on fossil fuels, your doom is right over here in another 20-25 years. If you can manage your affairs with less energy, you can extend it. If you can use hydroelectric power or solar power, you have a longer lease of life. And if you can tap nuclear energy in a safe and secure way, including conversion of thorium into uranium, then you have a much brighter future. How do you control your energy? You have a future if and only if you can control the amount of matter you use and the amount of energy you take. And that is the business of green chemistry. So, chemical revolution alone will ensure your survival on the surface of this planet. There is no doubt of it.
Yeah, also that is definitely going to reshape. In fact, we have to reshape our lifestyle through chemistry so that we can have sustainable development and survive on Earth. There is one simple. What are the other opportunities other than teaching profession in chemistry? What are the other job opportunities? Sai Mahajan wants to know that.
The world is full of requirements for chemists everywhere. Teaching is one noble act. But teaching in the teaching version, we do only laboratory. But when you make 1 milligram in the laboratory or 2 milligram, we have to make kilograms. So just be done in the industrial setting. So chemical industry and chemical engineering is a huge field, and the success of that field will give you. I give you an idea. India itself, what is the scope of the chemical market? So there are innumerable possibilities of, in fact, making a good soap for your buck itself is a startup and a brave new. Chemists are full of opportunities. Everywhere you can find, just look at it, you will find a chemical opportunity for it.
One last question which I have is, what is the latest innovation in chemistry you would like to highlight?
I would like to highlight targeted molecular medicine for certain diseases, particularly for leprosy, tuberculosis, and cancer. This is a scourge, and if particularly cancer is multiplying maddeningly, and the chemotherapy which we are using is not producing the intended results. We are able to extend the life of a diagnosed patient only 4 to 5 years. And when it is detected at the age of 35, and you are going to have
It
a
is
death warrant
possible
at
for
40,
ionizing
and five
radiation.
years only ahead of us, there is something wrong with our drug delivery system.
Light
So
absorption
if you
is
can
constant.
design a designer molecule which can go and attack the site correctly and remove it permanently from, that is what chemistry is, extension of quality life for patients, of all diseases. And for orphan diseases, there are certain diseases which are rare but suffering very heavily. We are not addressing those problems. So, the giving life, healthy life to sick people, and that is where chemistry, nanochemistry, and quantum chemistry for designing drugs, drug chemistry will be the thing that will be the most promising in the next 4 to 5 years. It will establish itself.
I think I could see one raised hand by Krishna Panchal. Do you have a question, Krishna ji?
Yes, sir.
Please ask your question.
So, the lecture, the information given by doctor was really very much informative and very much helpful. But I would like to ask a question. In your future, as a science student, what would have a better scope for engineering? Let's do it.
Can you repeat the question once
Your
again?
audio is not clear, Krishna ma'am.
As a science student in next future, which field will have a better scope in engineering?
Better scope of
In
engineering.
engineering, yes, sir.
See, there are two things between science, technology, and engineering. You can have a scientific mind, but you need an engineering mindset. It is not that you become a scientist or you become an engineer. What is required in practical life is think scientifically, critically, evaluate in a logical way. That is the analysis portion. Then do it with an engineering mindset to, to produce a product or a service. So therefore,
Can we check
our
the price
education
chart
now
of
is in
Diwali
the silos,
Chemistry?
physics, chemistry, biology, mathematics, STEM. But you look at physics and chemistry. In between, you have physical chemistry, you have chemical physics, and then you have chemistry. So between physics and chemistry, you have a broad spectrum. It is not that each one is a silo. And engineering is an extension of chemistry. From chemistry, you have practical chemistry, you have applied chemistry, then you have project chemistry, and you have industrial chemistry. That's the spectrum it is. So it should be the duty of a student of science to find out the scientific mind first, analysis, and then delivery. That is what the engineering mindset comes. Of course, you need ethics much later. That's a different story. So don't see yourself as a scientist or an engineer. What society needs, what humanity needs. Keep that larger perspective. If sustainable chemical engineering is required, develop processes and products which are meeting with that. So, but as you rightly said, till 12th standard, you should have a strong foundation, science, engineering, technology, and maths. Remember, mathematics and numeracy is very, very important in chemistry. Biology has been
सुन
descriptive.
रहे हो?
Chemistry also has been descriptive. But today we have chemical processes which are written down in chemical engineering. So numeracy in chemistry is very, very necessary for practical applications. Chemical literacy and chemical numeracy are important, and from that, say just a small step forward to chemical engineering.
Okay, thank you, sir.
Okay. Sir,
Okay, with this, yeah,
Venisha from Innovation Hub want to ask question.
yeah, please.
So, going deep into the nuclear science, I wanted to ask, we have 22 reactors and 7 power nuclear power points in India, but we only produce 3% of electricity from it. Why do we do that? We always say that we shouldn't use less coal to produce electricity. Then why don't we use nuclear for that?
Yes. Good question. Should be asked to the government of India, because this is only the policy of the government decides whether we should have how many reactors. It needs money. You need crores of money for building it. So the government will decide, I can give only this much money for you to work on that. Scientists and engineers will work on that. So these are national policies and national priorities. Just because something is good, we cannot spend all the money on that. There are other demands on the society. For example, hospitals. We need to give money to hospitals. And we need money for several educational programs. Good schools have to be built. Shall we have 1,000 schools or one nuclear reactor? So you will have to think of things from the scale of the government point of view. At the moment, education is most important. Let us have 10,000 schools. Let us have 1,000 universities. And let us have only 2 reactors this time. So what the society needs is not decided. Nuclear engineer will say nuclear energy is the best. Give me all the money in the world. Think of a world full of nuclear energy with no schools, no hospitals. So there is a proportion, there's a golden proportion among our various desires. And that is decided by the higher authorities at the government. They will decide what is to be done, what is not to be done, when it is to be done, how much is to be done. That's a management principle. And that is how society is managed.
There's one more, I think this we can take last by Yurjan Doctor.
Yes, sir. I wanted to ask what is the difference between quantum physics and quantum chemistry?
Yeah. It's a very quantum question, like my Schrodinger's cat. It began with quantum physics. The intellectual foundations and the mathematical framework for quantum theory was developed by Heisenberg's uncertainty principle. When Heisenberg said that there is an uncertainty, everything became confusion, everything became uncertain. In fact, science for a moment lost its certainty. But when Heisenberg mentioned in his theory that the product of two uncertainties is a constant, the position and velocity of a particle cannot be determined accurately and simultaneously. But when he said the product of two uncertainties is a constant, he has defined uncertainty in certain terms. So that is the physics of uncertainty. But from there, it is the radioactive decay of the atom. Is this atom alive or dead at this point of time? There's an uncertainty. That is how the metaphor of the Schrodinger cat came. So we thought, but if an electron is not to be found here or there, and if you want a single electron transistor for a computer, in fact, today we are speaking about single electron transistors in computers, and that happens, you should know the position and momentum of an electron. So if there is an uncertainty, then the computer output will also be uncertain. So that is the theoretical portion of it. But today, from the physics aspect of it, we have been able to tame it to quantum chemistry, where the chemical reactions at the atomic level have been predictable and reproducible. So, from the physics to the predictability of chemistry and reproducibility, it has become quantum chemistry. And it is quantum biotechnology now, where the molecular dimensions of the drug molecule is being done. So that is how I expect the quantum drug chemistry will be the first in thing that will be helping us in the year to come. So from the pure theory of physics to the applied theory of chemistry to the delivered drug chemistry, we can see the growth of quantum HG as it stands.
So there is one student
Okay.
from just one student from Innovation Hub. He want to ask question.
Hello, sir.
Yeah, please go ahead.
Please.
Sir, I wanted to ask that how can I become a nuclear scientist?
That's very easy. But first you think whether it's the one which you want to become. Because I take this decision only when you are in the 12th standard or 10th standard. After 10th standard, you will see the spectrum of subjects available to you. And you will also know the number of the marks you are getting from your examinations. So it's too early. Just because your next door neighbor is a nuclear scientist, don't become that. Another neighbor will be doing some other job. So there will be distracting professions trying to attract your attention. Keep cool. You can always become one at any point of time. But till you get your first degree, at the second stage only you do your BSc in physics or maths or chemistry, whatever. At that time you can apply this seriously by a literature survey, opportunities available, and whether you can have only one career in life. After 5 years of nuclear science, whether you want to change it to another, what will be, you started with nuclear physics, then you go into nuclear agriculture. So therefore, this is a too specific a personal decision for which there is no general antibiotic we can give. So take this decision quietly with your parents, with your teachers, with your consultants when you are in 10th to 12th. That's the right time to. Don't in 7th standard, 8th standard, don't try to take this decision and follow that one. The world is too colorful to be lost with nuclear science.
I think, okay, we can wind up now. We are already behind 15 minutes or more than that behind the schedule.
Sorry for exceeding the period.
uh, I think we can conclude now with a big thank you to Dr. A.P. Jayaraman. Yes, and thanks to all our participants. Thanks, see you all. That's how perhaps we can connect and take the message of science to millions, which is our slogan line in NCSM. So thank you all the students, all the teachers for joining. It's just on the eve of Diwali, I should say. I wish you all a very, very happy and green Diwali. Nowadays, that's the, because we are talking about green chemistry. Sir has already explained the chemistry of firecrackers also. So take care, be careful, and we are facing a lot of pollution problems. So wherever we can contribute, it is our responsibility. Happy Diwali to you once again. Thank you for joining us. See you in the next lecture. With this, we come to the conclusion of Chemistry Week. And today is also International Science Centers and Science Museum Day, and that is we celebrate on our anniversary. So there's a big celebration for us, you can say. Those who are in Science Center, they can witness the liquid nitrogen and other chemistry experiments live. And those who have missed, they can go on our Facebook page or YouTube. There you will find a lot of live experiments which we have performed during the week. Thank you very much for being here. And thank you, sir. Thank you very much for the wonderful talk.
Thank you, sir.
Namaskar.